I don't know.
Did you make them take the test or no?
Yeah, well, yeah, I wouldn't worry about him right now. Yeah. Let's just get through the semester, you know? Okay, so I have a review for the final. And what it is just a list of questions that you should look at from the entire semester out of the textbook. My intention is to make 90% of the test based on this, like problems from the book, all right? The other 10%, I might do some word problems or something like that. I don't really know lengthwise how long the test will be yet, but I plan on having it kind of narrowed down a little more by the next time we meet on Thursday. But I wanted to at least give you something right now for you to start to think about. So it's a lot of questions that are listed here. If I were in your shoes and I was handed this, I would say, all right, well, let me open up my old homework assignments, see which of these I've done. There are a few on here that were not in the homework. Like maybe I assigned number 53 in the homework, but I put it number 54 on here or something like that. I have been known in the past that if I give a review and it's a problem out of the book that has not been assigned before, that I've actually put that problem on the test. You know what I'm saying? So like, if I assign number 53 for homework and I put number 54 on here, like number 54 appears on the test, exactly the way it was written. So, and that's my way of gauging, like, are people actually going to do this, review this? If you do, then you might see the exact problem on the test. All right. What are we doing today? Polar coordinates. Polar. All right, polar coordinates. And have any of you ever heard of these before? Polar coordinates? No? All right, the word polar coordinates comes from the word pole, which refers back to our Cartesian plane. The origin, right here, this point, we call it the origin. In polar coordinates, that's referred to as the pole, all right? So let's see what the motivation of this is. And I need you to kind of step back and think kind of abstractly here a little bit. If you have a flat sheet of paper and you want to get to somewhere on that flat sheet of paper, like let's say you want to get to this point right here, and you're going to start here at the origin. The way that we've been taught to do it, or the way that we've learned to do it, is by asking for somebody to provide us two pieces of information. An x-coordinate and a y-coordinate, correct? And the x-coordinate will tell us how far to move along the x-axis, right? And then the y-coordinate will tell us how far to move up or down, which is parallel to the y-axis. So the distance, we can almost create ourselves a little drawing here where x is this, and y is this, and then this is the ordered pair, xy, right? And this is called a Cartesian point, all right? Cartesian. So that is our Cartesian coordinate system. So if you want to get to somewhere in two-dimensional space, somebody gives you two pieces of information. That is the x-coordinate and the y-coordinate, right? And that's the way we've been doing all of our math. But that's not the only way you could achieve the same result. So let's draw it again. Let's draw that same point. And tell me how else you could instruct somebody that's standing right here to get to that point. What's another way you could do it? Instead of giving them like how far to walk out along the x-axis, left or right, or how far to walk up and down parallel to the y-axis. What else could you tell them to get them out there? Can you think of anything you could do? So imagine you're like physically standing here, right? So we have to kind of imagine this is on the ground. So let's say that I'm standing at the origin. This is the x-axis, okay, like that. So my x-axis runs this way, right? And then my y-axis is like this, right? So it runs this way. And I'm trying to get to some point over there, right? So one way to do it would be provide me the x, right? And then I turn and then I walk out the y, and I'm there, right? But what's another way that you could get me from there to there? Straight to it, right? So what you would have to give me, though, first is some sort of like direction, right? Like which way to point, like, right? And then after you give me that direction, tell me how far to walk out, and I can get to that point, right? So what we do is we say that our reference, okay, our reference will always be this is the pole, okay? And we always start by looking out the x-axis. So when I'm standing here, what's up, Zach?
This is one of those days.
Okay, that's cool.
Just let you know.
Okay, thanks for letting me know.
I'm going to be here Thursday.
Okay.
But I'll be coughing all day today, and I don't want to interrupt your video.
Cool, thank you.
Sorry.
It's all right, thanks for letting me know. This way. Always starting this way. This is the way that polar coordinates are going to work. Okay, so I need to get to a point over there, right? So you're going to first provide me one piece of information, which is an angle to turn, which would, on our picture, be that angle, right? And then, once you provide me that angle, I need one more piece of information, which is the distance I walk out to that point. So we'll call that r, almost like radius, okay? With me? You still gave me two pieces of information, right? Whether I look at it this way, Cartesian, or I look at it this way, polar, I still need two pieces of information to get there. Yes? Okay, so this system right here is our polar system, and this point right here is still an ordered pair. It's still an ordered pair, but it's not xy anymore. It's always r theta. The first number is the radius, how far you walk out. The second number is the angle. And it's, you got to be careful. You can't flip this. If you flip it, it changes what it means, right? Understand that? Just like over there, if you flip x and y, you're in a different place. So this is an ordered pair, but in polar coordinates, it tells you how far to walk out, what angle to turn. Yes? Okay. Now, why is this useful? Like, why would we want a different coordinate system? Let me show you why it's useful, all right? What would this look like over here? You know what, let's do, I'll start with a new grid here. Let's practice putting some points out there, then I'll show you why it's useful, okay? So I'd like for us right now to do this example. Plot these polar points. Now, I had to tell you they were polar points, because if I didn't tell you they were polar points, then for all you know they're Cartesian, right? So now we have to be very specific. When we write an ordered pair up there, are we talking Cartesian or polar? So I'm telling you, plot these polar points. So the first one, 2, 0. So what am I going to do? The radius is 2. So that's how far I'm going to walk out, right? And what's my angle? 0 degrees or 0 radians. That means I'm just going to stand here and walk out 2 units, which is going to be here, right? I'll label that point A. Is that okay? That's point A. All right. You know what? It's kind of weird, but that's also the same thing you get if it was Cartesian, isn't it? Like if this was Cartesian, you get the same point. It's just, that's coincidental. That only works for certain points. Let's try this one. How about 3 pi over 2? Where am I going to be there? Straight up. Okay, so I'm going to turn by pi over 2 straight up and walk out 3. 1, 2, 3. That's the point B. Make sense? Okay. How about this one? C, -1, 3 pi over 2. Now we don't usually have negative radiuses, right? We don't usually have a negative radius, but with polar you can have a negative r. So don't think about it as radius like it has to be positive. Just think about it as telling you how far to walk out. So if it's -1, what does that mean? I'm going to move backwards 1 unit. But what angle do I have to turn to? 3 pi over 2, right? So I'm going to go 3 pi over 2, which is going to face me down, right? And then walk backwards 1, right? So I'm going to go 3 pi over 2, which puts me here. So now I'm facing that direction, and I walk backwards 1, which puts me right there. Understand? It's just a different way to move around, right? So you might be asking yourself, like, why, right? Like, why would you need polar coordinates? Do you see anything useful about it? And we could have got to all these points in Cartesian, right? What would these points in Cartesian have been? In Cartesian, it would have been 2, 0, right? This one would have been 0, 3, and this one would have been 0, 1, right? That's what they would have been. Agreed? Okay, so why is this useful? Well, do you want to know like the big picture usefulness of it? I can show you like the big picture usefulness. Okay. I just don't know how far out there I want to go here. Let me see if I can draw this, and let me see if you can see it or not first. Okay, can you see like 3-dimensional space there?
Yeah.
Do you all see that this is the XY plane, the standard XY plane, kind of laying down on the ground? And now I have a third axis coming out of the page? Yes? Okay. Later on in the calculus sequence, what we do is we define surfaces. So you've dealt with functions, haven't you? Like functions of parabola, lines, these different types of functions, right? But they all live on a flat sheet of paper. So later on in calculus, we deal with functions that live in 3-dimensional space. So imagine just like this sheet that's kind of waving around in the wind, right? And you just kind of freeze frame, and you've got this weird surface up here, right? What we do in calculus is we ask ourselves, if you were to project this surface down onto the ground, right? Let's say that you have a rectangle down here like this. Do you see the rectangle on the ground? And what you ask yourself, what we ask ourselves in calculus is, if you take that surface and you imagine like all the points in this rectangle going up into that surface, and we ask ourselves, what's the volume of that solid? And this can be any shape up here. It's a very difficult question in general to answer this. But in calculus, we have a way of doing it. So what I want you to focus your attention on is this region on the ground, okay? I'm going to draw that region on the ground over here on a flat sheet, like on a flat page. Are y'all following me so far visually? Okay, so if I take this region that's on the ground, it would look like this. Here's my x, here's my y. And let me give you some values just to make this a little easier to see it. Let's say that's 1 and that's 4. Let's say that's 1 and that's 6. Okay? 1 and 4, 1 and 6 there. Then would you agree that these points that live in here, those points that live in there, all have to satisfy these two things? X has to be between 1 and 4, and y has to be between 1 and 6. So every point in here satisfies both of these inequalities. The x-coordinate is between 1 and 4, but at the same time the y-coordinate is between 1 and 6. Yes? Okay. This region right here is called a Cartesian rectangle. Well, it's a rectangle, the rectangle you've always known your whole life, right? But it's a Cartesian rectangle because it's one of the inputs, right? Your Cartesian required two inputs, an x-coordinate and a y-coordinate. If you stick your x-coordinate between two constants and your y-coordinate between two constants, then you get a standard rectangle in Cartesian coordinates. And later on, we use that to find something like this, volume underneath this. Let me give you a more difficult problem, though. All right? So let's do this. I'm going to draw a different picture over here. What if I had like a sphere? Okay, imagine I had some sort of spherish, three-dimensional thing. Let me do it again since y'all aren't writing this down. Let me draw it. It's better if I start with the sphere. Okay, let's say I have a sphere. So here's like the x, and then here's the y, and then here's the z. Can y'all still see it? It's a little weird looking, but there's my sphere. And let's say that I just want to take a piece of that sphere, maybe just this top little cap, like right here. Okay, so understand that that's got a little bit of like a dome to it. And I want to project that down and then find the volume underneath that. Same question, right? What would the shape be on the ground? It would be a circle, wouldn't it? It would be a circle on the ground. So all these points in here would look like this. You would have on the ground a circle like this, and we're trying to represent all these points. Yes? And let me give you some values. Let me just say this goes out to 3, and this is -3 here. Of course, 3 up here and -3 down here. So a standard circle with radius 3, yeah? Could you represent that in Cartesian by doing something like I did before? Can you do it that way? Easily. Like if you're a point in here, then can you give me 2 restrictions on each of these that would force us to draw that disk? Any, do you think it would happen or no? What is your instinct telling you? That it's possible or not? No? If it was possible, what are you thinking we would put here? What are your... -3, 3? Let's just see if that works. -3, 3, -3, 3. Okay? This does not work. And let me show you why. Because this green is what that does. And see, there's points out here that would be between -3 and 3 xy's and between -3 and 3 in the y, but still live outside this disk, so it doesn't work. So it's going to be very difficult for us to describe that region. Understand? In Cartesian, it's not that simple. But what about if we look at it in terms of polar coordinates? So imagine you're standing here and you're trying to give somebody instructions on how to get to all these points. Right? What would you tell them? To fill up that disk, how far would you want to walk out? Anywhere from 0 to what? 3. Anywhere in between there, right? And then you want to be able to do what? Turn between 0 and all the way around, right? So it's kind of like this. Cartesian falls apart here, but if I do r and theta instead, polar, then if I say my radius is going to be between 0 and 3, that means I can only walk out that far, right? But then my angle is between 0 and 2 pi. Then what I'll do is I'll say, okay, I can start here, I can walk out like that, back and forth. I can turn a little bit, walk out, turn a little bit, walk out, turn, all the way around until I get back to 2 pi, and I've drawn the whole disk. Understand that? And you see, it's a very simple way of explaining that region in polar coordinates. In Cartesian, it's not easy. It's possible, but it's not easy. What we do, we actually, if you wanted to know what you would do here for Cartesian, is that you still trap your x between -3 and 3. So you allow your x to move back and forth, but you have to trap your y between square root of 9 minus x squared, negative square root of 9 minus x squared, and positive 9 minus square root of x squared. So that's basically the equation of this circle solved for y. The equation of that circle hopefully looks familiar because this is going to be on your final. That's the equation of that circle, x squared plus y squared equals 9. And if you solve this for y, you'd move the x squared over, so subtract it, and you take the square root, you'd have plus or minus. The positive part draws the upper part of the circle, and the negative part draws the bottom part, and you want your y's to be between those. So that would be the inequalities you would have to set up if you were in Cartesian. But notice that your y value is very complicated because it depends on the x. Where in polar, everything's between constants. And this becomes very nice to deal with. So what we actually do in calculus later is we have a problem and we say, man, this is tough in Cartesian. So let's convert it to polar, and the problem becomes easy. Does that make sense? And this happens for both, when you're in two-dimensional space, you basically have Cartesian or you have polar. Those are your two choices. When you go to three-dimensional space, you have Cartesian, you have what's called cylindrical, and you also have spherical coordinates. So there's three different coordinate systems that we can use in three-dimensional space. There's only two in two-dimensional space. So just so you know, I mean, this is, again, as we get towards the end of the semester, I'm more trying to get you to understand some concepts rather than I'm going to test you on this. All right. Have I at least sold you on the idea that it can be useful? All right, let's set up the main relationships, because Cartesian and polar, they are related to one another, but let's talk about their relationships. So I'm going to draw kind of the master picture here of our situation. If we have two-dimensional space and somebody supplies us with a point, then in Cartesian, we have x and y, and that would be the point xy, right? In Cartesian. So Cartesian is going to be in blue here. Now, in polar, which I'm going to do it in red, I guess. In polar, the things that are important are that distance. Heads up. I could hit anybody with that. Oh, don't worry about it. Just let it be. In polar, the things that I'm interested in are this distance, which we call r, and this angle, which we call theta, right? And then I have the polar point, r theta. Can you give me some relationships from stuff we've learned this semester? Some relationships between Those things? Any relationship that you can think of that connects the polar and Cartesian stuff together. Say it again. Very good. This is a right triangle, isn't it? So we know that x squared plus y squared must be r squared. These are things we've already established before, haven't we? That is a relationship. That relates in polar, right? In Cartesian, this number and this number, if you take those numbers and square them, that should be equal to that radius squared. What other relationships do we have? Give me something with theta. Sine theta would be y over r. I'm going to write it on the side here first. Sine theta would be y over r. We all agree with that? Let's solve that for y. So just multiply both sides by r. And what would you have? R sine theta is y. So let me write that relationship down. Y equals r sine theta. Okay? Any others? Can you give me a similar one, like for x instead? Cosine theta would be x over r, which would mean that x is r cosine theta. Okay, can you give me a formula that has theta and x and y only? No r. Because look, these equations have theta and they have x and y, but they also have r. Can you give me one that would not have r? What? Tangent theta. Agreed? Let me write it down over here. Tangent theta equals what? Y over x. Now, can you solve this for theta? Get theta by itself. What would you have to do to get theta by itself? Arctangent on both sides. So can I write this down? Theta equals arctangent of y over x. Yeah? You all with me? These are our main relationships. These are them. This is it. These four are the main relationships between polar and Cartesian. And if those are our relationships, then there must be some way that if somebody gives you a point in Cartesian, you can convert it to polar, or if someone gives you a point in polar, you can convert it to Cartesian. And that's what we want to do right now. All right? And we're going to use these relationships, all built off of just a simple right triangle. So let's now, for this example, convert this polar point to Cartesian. All right, first example. What was the first one I gave you? Was it 2, 0? 2, 0? Okay. So the 2 in this problem is the what? The 2 is the r, and then the 0 is the theta. So if I want to convert this over to Cartesian, that means I want to convert it over to xy instead, right? And what is the definition of x? X is, so this is r cosine theta. So that would be, what's r? 2, and then what's cosine of theta? Theta is 0, right? And then the y coordinate will be 2 sine of 0. You all see what I'm doing? And cosine, what is cosine of 0? 1, right? So 2 times 1 would be 2. And then sine of 0 is 0, and you get 0. Wait a minute, hold on. That's the same answer, isn't it? That I told you, sometimes this happens. It doesn't happen all the time. If you go back and you look at the picture that we have here for that point, polar says, this one says, don't turn, right? And just walk out 2. And this one in Cartesian says what? Walk out 2 and then don't go up and down. And you happen to get to the same point. So that one was kind of bad. Let's look at the next one though. Okay, the next one, what did I give you? It was it 3? So I gave you 3 and then pi over 2. So if we convert this to Cartesian, we're going to x and y, but that should be equal to, I'm going to write it like this time. It should be r cosine theta, r sine theta. So r for us here is 3 cosine of pi over 2, and then 3r, right, r, and then sine of pi over 2. What is cosine of pi over 2? Cosine of pi over 2? 0. So that's 0, right? And then what is sine of pi over 2? 1. 3 times 1 gives you 3, right? And does that match up with the Cartesian point when I drew it earlier? Right? And this says, hey, rotate by pi over 2 and walk out 3. But that's the same as doing this Cartesian. Let's look at that last one we had. It was -1 and then 3 pi over 2, wasn't it? Okay, if we convert this to Cartesian, to x and y, then it's going to be r. What's r for us here? -1 cosine of 3 pi over 2, and then -1, and then sine of 3 pi over 2. Okay. What is cosine of 3 pi over 2? 0, so it just zeroes this out. And then what is sine of 3 pi over 2? So -1, but then we multiply it times -1 and get +1. So 0, 1. Isn't that the point we had Cartesian? Okay. So see how that works? Going from Cartesian to polar. Let's do it the other way around now. Let's go from wait, did I just say going from Cartesian to polar? Yeah. I think I did. This is how you go from polar to Cartesian. Sorry. Now we're going to go from Cartesian to polar, which is a little more challenging. All right? So convert, I should be saying these, Cartesian points to polar. All right. And I'd like for you, well, I'm going to ask you to provide me some points, but let me start this off, all right? How about this one? How about the point 2, 2? So that's a Cartesian point. That means go out 2, up 2, right? Well, to go to polar, it needs to go to r theta, doesn't it? R theta? Okay, so we have a formula for r, don't we? Well, we have a formula for r squared, which is good enough because we can square root it at the end. So we're going to take, to get r, we're going to take this squared plus this squared, right? And then take its square root. Yeah? Okay, so that's me solving this for r. So square root of 2 squared plus 2 squared. Good. And then I need to get theta. We have a formula for theta, don't we? It's arctangent of y over x, which is 2 over 2. Everyone follow what I'm doing here? All right, what is that first one? Root what? Root 8. And then what is arctangent of 1? So that means at what angle is your y coordinate over your x coordinate 1? At pi over 4. And? Okay, I'm glad you're bringing this up. Okay, there are two places where tangent is 1. It happens here, And it also happens back here, but why am I not looking back here? Because the restriction on arctangent, right? Okay, but as we're about to see, not in this example, but in another one, you have to pay attention to that, all right? So right now, we think the answer is pi over 4, right? Okay, so let's just double check it. If we do this in polar, it says to rotate by pi over 4, right? And walk out root 8, which should be out here. And we're going to land somewhere out here, aren't we? Does that coincide to this point in Cartesian? Out 2, up 2? Seems right, yes? Okay, we're good to go. This is fine. We always want to do that little check at the end to make sure that we're in the right quadrant, because you can have an issue like the next example. How about this one? How about negative 2, 2? Convert that one over to polar. So I'm going to go, r theta is where I'm headed, right? R is going to be the square root of negative 2 squared plus 2 squared. And then theta is arctangent of 2 over negative 2, right? What's the first part? Root 8 again, okay. And then we have arctangent of negative 1. So we're saying to ourselves, where is the ratio of the x and coordinate negative 1 on our circle, our unit circle? So where was that? It was here and here, right? Here and here? Do you agree? The x coordinate divided by the y, or sorry, the y coordinate divided by the x coordinate will be negative 1 there and negative 1 here. Now, if you're just looking at arctangent, you're not allowed to look over here, are you? Right? Arctangent is cutting you off. It's not allowing you to look over here. So if you were to do this on your calculator, what is your calculator going to spit out as an answer? Remember, arctangent's only defined between negative pi over 2 and pi over 2. So your calculator is going to say what? Negative pi over 4. This is going to be root 8 negative pi over 4. That's what your calculator would tell you. And you would be wrong. You have to understand where your point lies. So this is incorrect. Even though it's correct from the calculator, it's not correct in terms of the picture. Because what quadrant is this point in? It's over 2, up 2. It's up here. So it wanted this angle, right? It wanted that angle, not the other one. So we just need to recover that now. We just need to realize that and change this to be the correct angle, which should be 3 pi over 4? Okay.
Restrictions for the arc, either tangent or something, they don't matter in the coordinates?
Well, we're using the arctangent to try and recover an angle. That angle we can use to help us get the correct angle. It might be that it gives us the correct angle, but it also might be that it gives us an incorrect angle and we need the one that's directly across from it. We just have to understand where we are on the unit circle. This is the danger. When you go from polar to Cartesian, it's pretty straightforward. But when you go from Cartesian to polar, because we're using an inverse trig function to get there, you always have to pay attention to this part. All right, let's do another one. How about this one? -8, -3. That is a Cartesian point. It lies in which quadrant? Third quadrant, right? So I need to try and find its polar representation. And remember, the big picture of what we're doing here is we're saying 2, 3, 4, 5, 6, 7, 8. Here's -8. Here's 1, 2, 3. Here's a point, right? I would like to know what angle do I have to turn by, and then what distance do I have to walk out to get to that point? That's what I'm asking for. So we have r theta, right? The r part should be pretty straightforward. It's just square root of the sum of the coordinates squared. Or I should say the sum of the squares of the coordinates. And then we have to do arctangent of -3 over -8. So 64 plus 9, right? 73, root 73, whatever that is, we'll just leave it as root 73. That's how far we're going to walk out. What's the angle? Well, that's not a common angle. So you're going to need your calculator to do this. And let's do it in degree mode. So if anyone, has your calculator, if you have your calculator, I'd like for you to take arctangent of, you can change this to both positive because they were both negative, right? Negative over negative is going to be positive anyway. So do arctangent of 3/8 in degree mode and tell me what you get. What is it?
20.56.
28 or 20?
20.
20.56. Let's just say 20.6. All right, so this turns into root 73 and then 20.6 degrees. And now what we do is we say, is this angle correct? Is it correct? No. Where does this arctangent think we are? Going back to this picture. It thinks we went out this way 8 and up 3 this way. That's what it thinks we did. Went out like this and up like that. Because at that point, 8, 3 has the same information when you do arctangent, right? It has the same information, the 3 divided by the 8. So your arctangent thinks we're over here. So how can we recover that? How can we change that? Just add 180 to it, right? And then it'll drop us off over where we need to be. So if we add 180 to this, so we've got root 73 and then 200.6 degrees. Make sense? I'm curious, would this be correct? So this is correct. We all agree with that? This one was not. Would this have worked? What do you think?
No.
Why not?
Because you're facing that direction and walking back.
Yeah, what direction would we be facing? 20.6, right? So we would be rotating 20.6, but instead of walking forward root 73, we'd walk backwards root 73 and we'd land at the same place. What I'm getting at is there's multiple representations for the same point in polar coordinates. These two are equivalent. Do you not like that? Okay, what about this? Can somebody give me another way to get there? I'm forcing you to use this. Can you get me there another way? You can use a negative angle, right? So instead of rotating by 200.6, you could go backwards and rotate by negative 179.4. Is that right? Hold on. No, negative 180, 169? Hold on, 59. 59, 159.4. What the heck are we doing there? How did that happen? What just happened? I forgot the negative. Right? So all we basically did was, instead of going this way around, right, 200.6, we just took 360 degrees away from that and came all the way back around and got negative 159.4. And aren't there just like an infinite number of ways to get to that point? You could take this right here, and you could do root 73, and then you could do 560.6 degrees, right? So what that would mean is, okay, like that's 0 degrees. I'm supposed to be back there, right? So that would tell me go like all the way around one time, and then stop, and then walk out root 73. What do y'all think? Okay. I will ask you on the final to convert from polar to Cartesian and Cartesian to polar. Polar equations. We were just talking about polar points, right? Now I want to talk about polar equations. And let me kind of start this off by asking you to recall some stuff. Recall Cartesian equations. Like this. That's a Cartesian equation, isn't it? That's an equation we've dealt with in the past. Our x's and our y's have always represented points on a graph. And so if I were to try if I were to ask you to just visually tell me what this would look like, all the solutions to this equation, you would say it looks like what? A line, right? This would be a line, visually. This is a linear equation. Yes? Okay, so this would be a line. Now, normally, you don't see it in this form. Normally, we solve for y, don't we? We get something like y equals negative 3/4 x plus 3. So that's what would happen if you like move the 3x over, and then you divide everything by 4, you would have that equation. That look more like a line to you? Y equals mx plus b? Okay, so that's a Cartesian equation. What are some other Cartesian equations we've had? Y equals, I don't know, x squared minus 3x plus 4. What's that? Parabola, right? Parabola. And then we had some Cartesian equations that were a little different. X squared plus y squared is 9. That's a circle, right? Radius 3, right? The first two equations right here are functions of x. Because if I graph those two, they would both pass the vertical line test. Do you all remember the vertical line test from college algebra? If I graphed a line or a parabola, this parabola opens up, doesn't it? So this one right here would be a line. It would have a negative slope, this negative slope. This one would be a parabola. It would open up because the leading coefficient here is positive. So if I use the vertical line test, these would both be functions, wouldn't they? Yeah? But this would not, because if you draw that circle, it would fail the vertical line test in multiple places. So functions of x, not a function of x. But circles are fun. I want to draw circles, and I want them to be functions. So maybe we can get a circle, maybe we can draw a circle with a polar equation. So here's the polar equations. So here's the actual, let me, just tell me, just guess if you can, what the equation of this is. I think you're on the right track. Maybe. You said something.
You just said the square root of 3 plus the square root of 3. Is that?
What did you do?
Because that's x squared plus y squared equals 9. But 9 isn't squared unless you want to do 18. Then x will be 3.
Not quite sure I'm following you. Not sure I'm following you.
What does it say? Never mind.
I think you're on the right track, but the connection that I'm looking for is not quite there yet. When we were converting Cartesian points over to polar points, we used the conversions, right? I would like for you to try and convert this circle from Cartesian, where it fails to be a function, over to polar. 3 what? What are you using? What can you tell me about a circle with radius 3? What do all the points have in common? What does every point on that circle have in common? The radius is what? 3. And the angle doesn't even matter anymore, does it? Right? Because if you use any angle, you're going to be on a circle. All the angles together will give you the whole circle, right? Okay, what were those conversions again? We boxed them up there. What was that? What was the first one? X squared plus y squared equals r squared. So if I rewrite this right here, replace x squared plus y squared with r squared, then that equation becomes this. Right? Agreed? And if I solve this for r, then I'm saying that r is equal to 3 or negative 3. So there are 2 polar equations that would draw that for you. Here they are. Now the one that we would normally use is this one, because when we talk about polar, we usually like our radius to be positive. But either one of these would work. And what you need to understand with this polar equation is that if I list, it's kind of like, do you remember in Cartesian, back here in Cartesian, if I wrote y equals 2 and asked you to graph this as a line, you would say it's a horizontal line up 2, because you're letting x be anything, right? And it just draws the whole line. Or if I write x is equal to negative 3, it's going to draw a vertical line, right? So when I'm here in polar and I write r equals 3, the theta is allowed to be anything, any theta. So this is just going to draw all the points that have a radius 3, which is going to draw the whole circle, isn't it? You with me? This is a very simple equation compared to this, right? I mean, isn't that much easier to look at? R equals 3 versus x squared plus y squared equals 9. Okay. Now I'm going to give you a picture and see if you can come up with the polar equation. Okay, so this right here is the circle radius 3. Okay, in other words, it came from x squared plus y squared is 9. All right, so now I'm going to give you a picture, and this is going to be in Cartesian. I'm going to draw you the picture of it, and I want you to see, I want to see if you can convert this to polar. This is that very special line, y equals x. Is there a way to turn that into Cartesian? I mean, to polar? Can you draw that line using polar coordinates instead of Cartesian? How? You need to know what? Okay. What do all those points have in common? Go ahead.
I was going to say, can we do like plus or minus infinity common and then do power 4 plus, like write an equation, pi over 4 plus n pi?
Your pi over 4 is, you're on the right track here. Very close. I'm going to ask you to just think about this. For this circle, what did all the points have in common? What the radius was 3, and that's what our equation became. Radius is 3. For all these points, what do they all have in common in terms of polar? The angle. What's the angle for all? If you're going to go out to this point, what's your angle always going to be? Pi over 4, right? Your theta is always pi over 4. So if I just write that down, theta is pi over 4, and the radius is allowed to be free and do whatever it wants, then that means you're going to draw this line. Because if the radius is 0, where are you going to be? You're going to be here. What if the radius is 1? Up here. 2, 3, 4, negative 1. Back here. Negative 2, negative 3, negative 4. So your radius is free to move around and vary. You fix your angle at pi over 4, and you get this line. If you do it the other way and you fix the radius and let the angle vary, you're going to draw circles. Does that make sense? It is somewhat abstract, but I really want you to make this connection. So let me try and force it a different way. Okay. You know when you're learning how to graph points and you get this, you go online or wherever and you have got this graph paper? Y'all used graph paper before? What do they always give you to help you? All these lines, right? So they give you this one line right here, which is like that line right there, and let's say that that's 1. That's, the equation of that line is actually what? X equals 1, right? And then they give you another grid like this. And that's x equals 2. And then x equals 3, x equals 4. And then they give you some negative ones like this, right? And they got that. And then they come across with horizontal lines. And that's what? Y equals 1, 2, 3, 4, 5, right? Negative 1, negative 2, negative 3, negative 4, negative 5. And you get what's called Cartesian graph paper. Here, you're holding x to be constant and letting y vary. X constant, y vary. X constant, y vary. Y constant, x varies. Right? Y is constant, x varies. What would polar graph paper look like? What would polar graph paper look like? So I'm going to try it. Let's see. Here's my xy axes. Let's start with r. If we hold r constant, r is 1, what is it going to draw? And let theta vary. Circle radius 1. R is 2. Let theta vary. R is 3. Oh, shit. I missed. For those of you who are going to take me for Cal 1, you'll notice that my language gets worse as we progress through the sequence of calculus. So I haven't cussed much in here, have I? I cuss a lot in Cal 1 and Cal 2. So I'm just preparing you for that. I'm sorry. It's a problem. Okay, so there. So you see how this is what happens when you hold r to be 1, r to be 2, r to be 3. With me? Now, what would happen if you hold theta constant? Well, you're going to draw lines, right? This is theta is pi over 4, which would be, missed it. Okay, there, like that. How about another common angle, like maybe pi over 6 would be like this. Pi over 3 would be like that, right? And then I could do the other ones, you know, like 3 pi over 4 and get this like this. This is considered to be polar graph paper. Does that seem reasonable to you? And again, if you sit here and you talk about a little tiny region, like this little region right there,